Good evening, everyone. Welcome to today's Maths Talk. Today we have Dr. Eshita Mazumdar as a speaker. We welcome you, ma'am. She is presently an assistant professor at Ahmedabad University. Her primary research interests are combinatorics and number theory. Today's topic will be on optimal bounds on the growth of iterated sumsets. So if you have any questions in between the talk, feel free to unmute yourselves and ask the question directly. Otherwise, you can also leave it in the chat and we'll let the speaker know. So over to you, ma'am.
Yeah, thank you. Sneha, first of all, thanks a lot for giving me this opportunity to speak with all of you. So let me share the screen. Yeah. Well, today I'm going to, as Snehal says, that I'm going to talk about optimal bounds on the growth of iterated sumsets. So basically, it's a basic and fundamental questions in additive combinatorics is to study the growth of iterated sumsets, and I have worked on that. So I just wanted to discuss with you those things. So let's begin the talk with some basic notations. So throughout this talk, mainly whenever I will say, I use the notation G. It means it's a abelian group. The structure imposed on it is an additive structure, and 0 being my identity element of the group. So when I take two sets, subsets of the group, then I define the sum set of A and B to be like this. It's a set containing A plus B, where the first A will belong to A and the element B will belong to B. So when I take A to be equal to B, this sum set will be denoted by 2A. So similar way, if I take, if I wanted to define 3A, so that means I have to consider A plus 2A. So in other way, for H greater than equal to 2, I can define HA to be A plus H minus 1 of A. And this is known as H-fold iterated sumset of A. So here I have defined it for H greater than equal to 2. So for H equal to 1, basically we are taking it to be A. And for H equal to 0, it's the set containing the identity element of the group. Now, in additive combinatorics, it is very, very important question to understand the cardinality of HA. As we are growing with H. And as I said, my main aim is to study that thing. So suppose I have already the cardinality of HA. So I wanted to estimate the cardinality of H plus 1A or H minus 1 of A. So in this regard, in 1970, there was a classical theorem given by Clunake, and he said that suppose I have a abelian group G, and A being my finite subset of G, then we can say that cardinality of IA is greater than equal to cardinality of HA power I by H. Here I is running between this 1 to H. Okay. And this inequality Clunake established using graph theory. So this inequality is basically equivalent of saying that cardinality of H minus 1A is greater than equal to cardinality of H power H minus 1 H. Now, what is our aim? Our main aim is to strengthen, recover and strengthen this estimate. And for doing that, here we are using completely different approach, which, though commutative algebra has been used earlier in additive combinatorics, but this approach is never used in additive combinatorics. So what we are trying to do is that since we have a set A in our hand, so we wanted to construct a corresponding standard graded algebra, RE. And then we will show that the corresponding Hilbert functions are nothing but the sequence of cardinality of H. And then we wanted to just use the Maculus theorem on this growth of Hilbert function. So we claim that using this, if we actually going through this approach, we will have a better bound than Unity. So before going into that construction, let me define a few things. First of all, let me introduce the standard graded algebra. So suppose I have a commutative algebra over the field K, then the standard graded algebra is nothing but it's a decomposition of R in Ri's, where it should satisfy the three conditions. First of all, R0 should be the field, Ri, Rj should be subset of Ri plus j, and R is generated as a K algebra by finitely many elements of R1. So let's say I have a standard graded algebra. Now, once I have standard graded algebra, I can talk about the Hilbert function of it. So I have the standard graded algebra. So it has a finite dimension. Each Ri has a finite dimension. So I can define this as each dimension I'm denoting by di. So the mapping I goes to di. This is called a Hilbert function. Okay. I hope up to that much is okay to all of you. Okay, let me proceed. Okay. Now I'm going to introduce the definition of binomial representation. Suppose I have two positive integers, a and I, so that a is greater than equal to I, greater than equal to 1, then there are unique integers. We can say that there are unique integers in the increasing order, so that a can be written as in this binomial expression, like a is equal to summation of aj cj, where j is running from 1 to I. Now this binomial representation, so this is the binomial. Once we have this binomial representation for A, we can define a new factor here, which we denoted by AI. And that is nothing but the summation of aj plus 1 c j plus 1, where j is running from 1 to I. Once we take a to be equal to 0, we denote, we take its value to be equal to 0. One example I'm taking a to be equal to 100, and I'm taking I to be equal to 5. One can see that its value will be 152. Now, how I'm doing it here? So I have A to be equal to 100 and I to be equal to 5. So 100 can be written as this way. Okay. So these are my AIs. And once I have this, I can calculate 105, this function. So if we take these values, one will have 152. Okay. Now let's see that if I have a group, if I have a group and let's say I have a non-empty finite subset of subset A, and let's say I have a community, I have a field, then how can I construct a standard graded algebra so that its Hilbert functions should be cardinality of AG? Now let's see that, how to do that. Since I have a group, I definitely talk about the group algebra, which is my KG. And since so KG is a group algebra, so it has a canonical K basis, which is the set of symbol. I can write it like T power G in this form. And I'm taking it so that product induced here is nothing but T power G1 plus G2. Now let me consider the one variable polynomial algebra over KG, which I am denoting by S. Clearly, this S has a natural K basis, which is T power G x to the power n, where G is from my group and n is from the set of natural number. If I take two basis element, then their product is given by, let's say I'm taking Tg1 x to the power n1 and Tg2 x to the power n2, then it is nothing but Tg1 plus G2 x power n1 plus n2. And this will happen for any Gi in G and for any Ni's in the set of natural number. And for any element from this basis element, suppose I'm taking this basis element, then the degree of this basis element is denoted as n. So clearly, if I have a group G, so I can construct S, I can say that this S, which is a direct product of SH, this is my graded K algebra. And this SH has a vector, K vector space with the basis Tg x to the power h. Now, once I have this, now we know that I have a finite set A. So G is my group, I have a finite set A. So A is my, let's say A is my set A1 to AN. Now since I have S to be a graded algebra, standard graded algebra, so I'm considering the subalgebra RA, which is generated by these elements. What are the elements? It's the TA1x in this way, TANX. So my RA is nothing but this thing. Clear? So since RA is finitely generated over K by elements of degree 1, it is also a standard graded algebra. And so we have R to be of direct sum of RH. What is RH here? RH is the vector K vector space, which has the basis set TB x to the power h. And this B belongs to HA. This ensured that the dimension of this RH would be cardinality of HA. So this is the way how we can, so I have a group, so, and I have a set. Now I associate a standard graded algebra RA, whose Hilbert function is exactly same as the cardinality of HA. Now, what will be our next step? Our next step is that we need to apply the Maculus theorem. So, in 1927, Maculus stated that suppose the numerical function I goes to di is the Hilbert function of a standard graded algebra. Then it's the necessary and sufficient condition for that will be this di should satisfy this thing. D0 has to be 1 and di plus 1 should be upper bounded by this quantity, which is di I. And this should happen for all I greater than equal to 1. Now, we are taking only the necessary part of this. So, I have a abelian group G, and I'm taking A to be a finite subset. So, I'm considering the sequence HA. I can associate a standard graded algebra whose Hilbert function will be this HA. And Maculus theorem ensured that it should have satisfy this thing. That means we will have this inequality. So it is cardinality of H plus 1 into A is less than equal to cardinality of HA, H. And this should happen for all integer H greater than equal to 1. Now, one can see that it's a similar result which we have in the Plunake inequality as well. But not only that, we can have, we also have a condensed version of Maculus theorem. And from there also, we can say about the bound of this cardinality of H plus 1A. So here, suppose I have a natural number H, and let's say I'm taking a real number X. Then here we are denoting XH, this binomial XH is nothing but the real number, which is X into X minus 1 up to X minus H plus 1 by factorial H. Now in 2018, Salam Eliyahu, he proved that if we have a standard graded algebra R, whose Hilbert function will be di, then there is a unique real number X greater than equal to H minus 1. If there is a unique real number X which is greater than H minus 1 such that dH is equal to XH, then we can say that dH minus 1 is greater than equal to binomial of X minus 1, H minus 1, and dH plus 1 is less than equal to X plus 1, H plus 1. Now, using this condensed version of Maculus theorem, what we can conclude here is the following. So, as I mentioned, we have the group, abelian group, and I have its non-intersect A. We can make a standard graded algebra RA, whose Hilbert function is HA, and this can be written as this. If X is a unique real number, then we can conclude that cardinality of H minus 1A is greater than equal to X minus 1, H minus 1. So you can see that here. Just a second. Yeah. Okay. I'm just replacing dH minus 1 by cardinality of H minus 1A. And for cardinality of H plus 1, I consider it has the upper bound, which is X plus 1, H plus 1. Now, we can see that we here we have an upper bound, and also in the previous theorem, we got an upper bound, which is cardinality of H. Now, it has been observed that for x greater than equal to H, if cardinality of HA is XH, then the previous upper bound is smaller than this upper bound. So basically, the last upper bound which we get, that is a more stronger upper bound than this one as well. Now let's discuss these things, that how stronger these are through an example. So I'm taking any abelian group, and I'm taking a finite subset, so that cardinality of 5A is my 100. Using the Plunake inequality, we just have that cardinality of 4A is has lower bound 40, and cardinality of 6A has upper bound 251. Now, using the condensed version of Maculus theorem, what we will have is that we can increase the lower bound 40 to 58, and our upper bound will decrease up to 161, which is a quite good upper bound. So this is definitely condensed version of Maculus theorem is stronger. Now further, we observe that the result which we got from the Maculus theorem, that will be the most that will give us the most sharper bound. It says that cardinality of 4A has a lower bound 61, and cardinality of 6A has a upper bound 152, which is much better than the bound which we are getting from the condensed version of Maculus theorem. Now, okay, is there anybody has any questions or something like that? Okay, I hope till now nobody has any question. So once we have this observation, a natural extremal problem will come into the mind, that how far our bounds are, I mean, whether our bounds are the optimal ones or not, basically. So what we wanted to know that is that whether the equality will happen here or not. Well, in this case, for that, investigating that, we introduce a extremal function which we denoted by omega g of HIM, where HIM a positive integer, and it is taking the value minimum of cardinality of IA for I less than equal to H, and it is taking the value maximum of cardinality of IA for I greater than equal to H. And the extremum is taken over all subset A of G, satisfying cardinality of HA equal to M. Now, what we have this bound, and if we wanted to write down this bound in terms of omega, then basically we have omega g of 5,400, that is greater than equal to 61, and omega g of 5,600, that is upper bounded by 152. Now, if we consider our group to be Z, and if we take a particular set, let's say A containing 0, 1, 5, 8, 49, then we observe that for this particular set, cardinality of 5A is 100, cardinality of 4A is 63, and cardinality of 6A is 145. And what we are hoping is that is a conjecture, and it's a really strong conjecture after seeing this, that we are hoping that this bound, the value we are having here, that is the optimal one. Okay, so I mean, whatever set you will take with this, you will have this exact value. It's a quite strong conjecture we are hoping here. Okay. Now, well, this is an external problem. It's coming up from here, but now let's go back to our previous one, previous analysis of the upper bounds, and let me introduce here a new function. So for the positive integer h and the real number x greater than equal to h, I'm setting theta xh to be h by x binomial of xh power 1 by h. Okay. Now, from the condensed version of Maculus theorem will give me and bound for lower bound and upper bound, and that we can write it in this form. In other words, we can say that if A be any non-empty finite subset of W with G, then for h greater than equal to 2, this will happen. Where x is a real number satisfying cardinality of HA is xh. Moreover, we have that theta is greater than equal to 1. And this thing ensured that it is basically this result, this condensed version is basically stronger than the Maculus theorem. Once we have that derivation, this calculation is very easy. We have this cardinality of h minus 1 of A is greater than equal to x minus 1, h minus 1. And this you can easily write down as this h by x of binomial of x h. This can be written in this format, which is x by h into x minus 1, h minus 1. And that will, if you replace it here, that will eventually give you the result. And on the other hand, since we know that this will satisfy here, this will conclude that here theta power h is greater than equal to 1. So theta will be greater than 1. And that proves the result here, this one. Okay. Now coming into the other version as well. Now theta is my, once I have the real number, that cardinality of HA is the binomial of XH, then theta, which is x by h, xh power 1 by h, can be written as this form as well, that is h by x, cardinality of h power 1 by h. And from here, we can give another version which says that cardinality of h minus 1a is greater than equal to h by x, cardinality of h. Clearly, here x is a real number satisfying cardinality of h to be xh. Now let's talk with the properties of theta, some other property. It has very nice properties. One of the properties is that whenever you will take x to be strictly greater than h, we will always find the value of theta to be lying between 1 and it will always lie between 1 and 2. The second thing, it's saying that, so let's say I'm fixing this h, fixing this h, and I'm varying my x, then we will find that this theta is a strictly increasing function. It also has asymptotic behavior for larger values of x. It is asymptotically same as this quantity, and as it extends into infinity, well, the proof of this can be done using the Stirling formula. So, if you see, I'm drawing this theta for a particular value of x. So I'm taking x to be equal to 1000, then and I'm varying my age to 1 to 1000. Then one will find that its value, it is varying like that. It's first increasing. Now the next property is saying that as x increases, theta x by 2 is tending towards 2. From here, you will have a glimpse of that. So this is actually 1000. So it's for the 500 somewhere here. Its value is actually tending to 2. And if you take if again for extending to infinity, if we consider theta x root x, then that basically tending towards well, here basically I will so this is the result which I have. It's the improvement of the Plunakis inequality, and from the Plunakis inequality, how I'm writing that there is a factor theta was involved there, and I discussed already the properties of theta. Now, the question is that from here, what we can see further. So let me remind once again that what we have proved. We have proved that for G to be an abelian group and A to be a finite subset of G, we have that if I consider this, if I set up that DH to be the cardinality of HA, then we have this inequality. And if I give a nice example, I can say that, okay, if I consider, let's say, any set A, and I've considered the cardinality of A to be 1000, then this my result will give you the upper bound to be 1827, whether the Plunaki bound will give a much larger value, that is 3162. So naturally, one question which one would have in mind is that whether this result which we have is the best possible, whether the upper bound is the best possible. So best possible in which sense? That is very important. Best possible in the sense that suppose I'm having a set of positive integers which is satisfying this property. Now I'm going back actually. So I have a sequence which is satisfying this property. Okay. And I just wanted to know that whether there is a commutative group, basically, because you know, here we are dealing with the abelian group. So definitely I will looking for a commutative group so that this will happen or not. Now, here, well, at this moment, it is quite difficult to say about abelian group, but if one observes, one can see that, well, since it is true for this statement is true for abelian group, so this statement with the same construction and everything being same, for this is true for abelian semigroup. So if I ask in the converse in this way, that if I have a sequence of integers, so that this will happen, then whether I will have commutative semi-group so that and a finite subset is such that this hold or not. Then in that case, we solve the problem and we say that yes, there exists a commutative semi-group, but till now we can't say about whether there exists any commutative group or not. Okay, so for doing that, first of all, we make some construction here. Since I have a sequence of integers, di's, let's say I'm taking n to be equal to d1. And I'm considering mh to be the set of monomials of degree h in this exercise. Well, here I'm giving a lexicographical order to this exercise. First of all, for degree 1, I'm fixing it to be x1 greater than x2 greater than x3, in this way xn. So for the order in mh would be like x1 power h greater than x1 power h minus 1, x2, in this way also xn power h. Now, there is a concept of a Lex segment in the set of monomials of degree h, which is those monomials of degree h such that this v is greater than equal to u for some u in mh. If also if L is a Lex segment, then this M1L, which is a subset of MH plus 1, this is also a Lex segment. There is another two things. The Lex segment have minimal growth. First of all, if B and L are both are subsets of MH and L is the Lex segment of length having the same length with B, then we can say that cardinality of M1L is less than equal to cardinality of M1L. One more property which a Lex segment has, that if L subset of MH is a Lex segment, then we can say that the complement of M1L, that cardinality is same as the cardinality of complement of L in MH. Now we have seen the Maculus theorem, which we have, we have seen the Maculus theorem, which is saying that if I have okay, so you can go back to just a second, Maculus theorem at the moment. So this is my Maculus theorem, right? The Maculus theorem is saying that if I have a standard graded algebra with the Hilbert function, then the necessary and sufficient condition is that this Hilbert function will satisfy this. So I have used here the necessary part. Now, what will be the converse part of it? So that I am considering it here. Okay. Yeah. So from the converse of Maculus theorem, we can say that okay, suppose I have a sequence sequence in set, in N, so that it satisfies this di plus 1 less than equal to dii. Then there is a graded algebra so that this will happen. Now, if you go to the more detail of the proof, one can identify that, not only that, we can say that there exists a lattice ideal L in Kx1 xn such that we can say that the Hilbert function for Ri is exactly same as this here. Okay. Now, let me introduce the Maculus theorem in additive notation as well. So for that, consider the group G, consider the semigroup G as n power n, and I'm taking B to be the canonical basis of G. So what is my EI? EI is I'm taking to be this, where this is 1 at the ith position. So if I consider HB, so this is nothing but the set of elements of G whose coordinate sum is equal to H. Now we can say that there is a theorem which explains that for H greater than equal to 1 and all subset A of HB, we have cardinality of H plus B is greater than equal to cardinality of ALX plus B, where ALX subset of HB denotes the unique segment of cardinality of, which has cardinality same as cardinality of. And this shows that Maculus theorem is also belong to the additive commutaries as well. Now, proving that theorem, what we are basically doing. So what we need to prove. So first try to understand that what let me just show you that we have a sequence of positive integers di, and we have di, this statement, we have this relation that di plus 1 is less than equal to di. We wanted to find out a commutative semigroup and a finite set here. Okay. So we have sequence di and we have this relation. Now here what we will do is that we make our construction of G and A is in the multiplicative notation. First of all, I'm taking n to be equal to d1 and I'm taking s to be equal to k x1 x2 xn. Now then G is nothing but my multiplicative submonoid of the quotient ring S by J, and J is a homogeneous ideal of S. Then I will take the quotient map from S to R and I will set Xj to be equal to pi of capital X. So if I have A, and then I will consider the subset A to be equal to x1 to xn, and its H4 iterated product set will be AH, since I am taking the multiplication notation here. So I will consider AH to be product of A's, this is H time, okay? Now, the main problem here is to uncover the suitable ideal G. So we have to find out the suitable ideal so that this equality will happen. Now, if we are looking for an almost sharp realization, suppose, then we just need to use the sufficient part of Necklace Theorem. But for the sharp realization, we need to deform J into some binomial ideal J star. And the last step will be done by using the concept of Grobner basis, as it preserves the Hilbert function of J. Okay. That's what is the what is an almost sharp realization says here. So suppose I have a sequence of integers so that d0 is equal to 1 and it satisfies di plus 1 is less than equal to di I. Then there exists an abelian semigroup G and a subset so that its cardinality of HA will be lying between DH and DH plus 1. So that is the reason why I'm saying it to be an almost sharp realization. So it is taking two values, either DH or DH. So let's see that why sometimes it can take the value DH plus 1. Well, for the notational purpose, I'm taking n to be equal to d1, s to be equal to k of x1, x2, xn, and m is a set of monomials of the form like this, x1 power a1 into xn power an minus. So the proof requires 3 facts about the monomial ideals. That is, the ideals is generated by monomials. First of all, we need a basic lemma. What does it say? It says that suppose J is a monomial ideal of S, then I'm taking let's say I'm taking F from S. What we can conclude is that F belongs to J if and only if every monomial with a non-zero coefficient in F belongs to J. And that is very obvious because J is spanned by the monomials U from M, and M is a K basis of S. Okay. Now, coming into our next proposition, which we need here, it says that suppose J is a monomial ideal of S, and pi is a quotient map, which is from S to S by J. Then the family F, which is pi U, U is the monomial, but U does not belong to J. This forms a basis, a K basis of S by J. Well, while doing this, what we need to do is the following. So F spans S by J, since M span S, as well as you can see that pi of M intersection J is this. Now, since F is this family F is free, so whenever I will write F in this format, and if I take pi of F to be equal to 0, then F has to belong to kernel of pi, which is nothing but my J. Now, using the lemma, the basic lemma, that will imply that lambda u will be 0 for all u in here. Therefore, F is equal to 0. Okay, so it forms a basis. Now, coming into our next proposition, now what it says. So suppose I have J to be the monomial ideal and I'm taking R to be S by J. I'm considering pi to be a mapping from S to S by J, and I'm setting Xj to be pi of capital Xj for all J. If I take my set A to be x1, x2, xn, which is a subset of R, then what we can conclude is the following, is that cardinality of A power h would be my jh is 0, and it is dimension of Rh plus 1 if this is not. Now let's see how the proof of this goes. Follows like this. So J can be written as direct sum of ji's, where ji is a vectors, okay. And this ji has a vector subspace which is mi intersection. Okay. Now since A is my pi mi, right? I'm taking A to be this, and you can see that mh is basically m1 power h. So we have that a power h to be pi of mh. Is the first point. Okay. Now the second point is that since j is equal to kernel of pi, we can say that pi of mh, this is equal to pi of mh minus j if their intersection is empty, and it is this union 0 if not, right? Now from here it follows that dimension of Rh is equal to cardinality of mh minus jh, and that is equal to this. And combining these three things, we can say that, okay, this happens that cardinality of AH would be this quantity. Okay. Now coming into the proof of the theorem. So what was the theorem? Let me recall once again. The same thing. We have the sequence of integers. This happened. We need to prove this. Now we have enough material with us. Now, from Maculus theorem will guarantee us that there exists a standard graded algebra so that this will happen. And the graded algebra whose Hilbert function will be DI. That ensures we get from the Maculus theorem. Not only that, we can choose the suitable Lex ideal, and we can say that R is equal to S pi L. Okay. Now, pi is a mapping from S to R. So I'm taking G to be pi of M. I'm setting Xj to be pi of Xj for all J, and A to be X1 expression, which is a subset of G. And it follows from the proposition that cardinality of AH belongs to the set dh plus 1. Okay. Now we are proceeding for the sharp realization. Now for the sharp realization, what we need is that we need a commutative semigroup, existence of a commutative semigroup. Now, how to do that? First of all, we now seek to realize the equality here. AH is equal to D. Okay. The main steps are the following. So I have pi, which is from S to S by L. This L is a monomial ideal. So dimension of RH is equal to DH. That much we have. We also have that pi of M is equal to pi M minus L union 0. The trouble here is the extra 0 accounting for cardinality of AH to be equal to DH plus 1 when this LH is not equal to 0. Now, what we need to do is that we seek to deform L into a homogeneous ideal L star with the following properties. so that we will have a pi star, which is from S to S by L star. And we have that dimension of RH star is same as dimension of RH, and pi star M would be same as pi star M minus L. So this is where we can avoid the extra zero. Okay. Here is how we do it. So we are taking the monomials UI. So let's say U1 into ER from M, and we are taking L. So be such that this is L is my geometry by this U1 R. Okay. Now we are deformed L to L star as by taking the differences U1 minus V1, U2 minus V2 in this way, UR minus VR. So where VR has some properties. The properties are the following. Vi belongs to M. Degree of Vi is same as degree of UI. UI has to be greater than Vi corresponding to the legs or the ring. Okay. UI minus Vi, in this way, UR minus VR. This is a Grobner basis for L star. Now, to be satisfied, this condition required a very careful choice of monomials Vi, but it can be done. Actually, we have done that. And now, as before, what we have concluded, we have that let A would be our pi star M1, which is a subset of R star. And from here, we will have cardinality of AH to be equal to pi star MH. And that will be same as dimension of RH star, and that is equal to DH. So this is the way how we will do our sharp realization. These are the procedures. Okay, and that include lot of degree. So I'm not presenting those things here at the moment. Okay. Now, once we solve this thing, so the next question, as I have told you, was that the upper bound here we are finding a sharp relative to the abelian semigroups. Now, what about the analogous sharp upper bound relative to abelian groups? Well, our conjecture was that it is possible to do that for the abelian group, but we don't know how to proceed in that case. Okay. Well, these are few references. The first part which I have discussed is that has been already accepted, and the second part we just submitted. So with that thing, I would like to finish my talk. Thanks a lot.
Thank you so much, ma'am, for such a wonderful talk. So I'll request the participants to ask any questions if you have. So feel free to ask any questions if you have. Okay, so I guess there are no more questions. So thank you very much, ma'am, for such a wonderful talk.